Right. Any questions from the previous class? Okay. Let's do a quick recap. In the last few classes, we were looking at this notion of pack learnability. So we say that a hypothesis class is agnostic pack learnable if for every epsilon and delta greater than or equal to 0, you can find some m, some positive integer m, and some algorithm, some learning algorithm, such that the learning algorithm outputs a HS for which the generalization error is within an epsilon of the best generalization error that you can achieve within this class. And this happens with a probability at least 1 minus delta. So the probability that the generalization error of the learning algorithm is greater than the best possible generalization error within the hypothesis class plus some epsilon. This particular probability is at most delta, right? And this holds true for all pxy, right? So irrespective of what the underlying ground truth is, you will always be able to achieve this as long as the number of samples that you have is at least this particular quantity, right? And the important thing to just keep in mind is that this particular integer, which we call the sample complexity, depends only on the hypothesis class, epsilon and delta. Of course, it implicitly depends on what is the learning algorithm, your loss function, but is otherwise independent of pxy, right? So this m is independent of pxy. There's a universal m which works for all possible ground truth distributions, right? And this is a fairly strong requirement because we're saying that even it doesn't matter what the ground truth is, this hypothesis class can always be learned to a desired accuracy as long as the number of samples is at least this particular quantity, right? And we saw that if you look at, let's say, finite concept classes, then all finite concept classes are pack learnable with sample complexity at most 1 over epsilon log the size of the hypothesis class divided by delta, right? So as long as you have those many samples, as long as your training set is at least of that size, it doesn't matter what classification problem you're looking at. If you have those many samples, then you will be able to achieve epsilon delta accuracy, right? And another way to look at it is, so one note that you don't really know what R of H star is, right? Because you don't know what is the best possible hypothesis within the class. But we know that if we use ERM and we have those many samples, then as long as you have a finite concept class, you can learn it. Another way of looking at this particular result is that if you have at least those many samples, if you have at least mh of epsilon comma delta many samples, and let's say you run this particular algorithm, then with high probability the empirical risk that you achieve will be very close to the actual generalization error for that particular h. And from this particular requirement, you know that the generalization error is at least epsilon close to the best possible generalization error that you can achieve. So one way of estimating this particular generalization error, the least possible generalization error, is you just look at the empirical risk, the final empirical risk that is achieved by the ERM. Of course, I'm making some simplifications over here. I'm assuming that the best possible algorithm is in fact ERM, which is not always true. Okay. All right. So again, a little bit of terminology. In general, if you have a hypothesis or if you have a ground truth that is described by an arbitrary joint distribution, then we say that H is agnostic pack learnable, just to signify that the minimum possible generalization error need not be equal to 0. But if you are in the realizable setting where it is in fact possible to achieve a generalization error of 0 for every px, then we simply say that the hypothesis class is pack learnable instead of using the term agnostic pack learnable. All right. ERM is an algorithm, right? If ERM succeeds, like if ERM allows you to achieve this for every pxy, then the hypothesis class is pack learnable, right? That's one learning algorithm. But just because ERM does not succeed does not necessarily mean that the hypothesis class is not pack learnable. No. For finite classes, yes, we know that ERM allows you to achieve an epsilon comma delta error, but in general you may not be able to achieve epsilon delta error for arbitrary epsilon and delta for potentially infinite hypothesis classes. We'll see a little bit of that in this particular class. So we say pack learnable if we are dealing with we are talking about the realizable setting. That is, we have a concept class, the hypothesis class is equal to the concept class. That's when we say that the hypothesis class is pack learnable, right? And in other words, the ground truth is actually something from your hypothesis class, or at least or a subset of the hypothesis. Then we say that it is pack learnable. In the more general case where the ground truth can be drawn according to any arbitrary distribution, any arbitrary joint distribution pxy, we say that it is agnostic pack learnable. Correct. We'll see later on, but for most of this course, we'll just deal with ERM. There are some variants of ERM. That's something we'll deal with later on, but SVM is something different. In SVM, again, you use some kind of an optimization algorithm.
And the algorithm is need not be correct.
Not necessarily. There could be multiple algorithms, there could be multiple learning algorithms that allow you to achieve epsilon delta error. Any other questions? But in fact, later on, we'll see that at least in the context of binary classification, if it is pack learnable, then ERM is actually allows you to achieve learnability. Okay, so we proved that as long as you have a multi-class classification problem, all finite concept classes are pack learnable.
The notion of algorithm is with respect to this R of.
So in this context, an algorithm is something which takes as input a sample, a training set, and outputs a function h from the hypothesis class. That is an algorithm. That is a learning algorithm, right? The actual function h that you output is the hypothesis, right? So, so this essentially is something that takes as input s and outputs h of s. ERM is one particular approach. Then you could formulate an optimization problem that outputs. Okay.
And if there are multiple algorithms which does that,
okay,
then how we will be able to know that which algorithm, how you can compare those?
In general, it depends, right? The first thing that you always try is use ERM. It's simple, right? And it's one of the most natural things that you would want to do. and it's also very easy to analyze. So as I said, we've proved that finite concept classes are pack learnable, but in fact you can also show that all finite hypothesis classes are agnostic pack learnable, and we'll see a little bit of that in this course. Agnostic means that the ground truth is not necessarily a concept, it is a joint distribution, Pxy.
Then y is also random.
Yes.
But
The conditional distribution, conditioned on x, y is still a random variable, a non-trivial random variable.
when it is pack learnable,
It is a concept class. So,
and
yeah.
agnostic is
So pack learnable if y is equal to c of x.
pack
It's a special case of agnostic pack learning. One can think of, like, the agnostic would essentially correspond to the fact that you don't know where the ground truth is coming from, right? In this case, you know that the ground truth is coming from the hypothesis class. So you have some background information about what the ground truth is. In this case, you know nothing. It could be a function. The concept class could be very different from the hypothesis class, or more generally, y could be a non-trivial random variable conditioned on x. In this case, when you say pack learnability, the ground truth is coming from the hypothesis class.
Then what about the algorithm which algorithm output that also belongs to the same?
Yeah. So whatever the learning algorithm always outputs something from the hypothesis class.
Algorithm output, but ground truth is not made.
Not necessarily something from the hypothesis. Okay. And we saw that in the general case, in the setup of agnostic pack learning, if we actually knew the ground truth, then the optimal thing to do would be to use the map estimate, which is also called the Bayes classifier.
Then y is also random.
Y is a random variable. I mean,
What is the input of this x? Really, we should write y of x.
I'm sorry, where?
P of h of x is not.
So this is according to the joint distribution on x comma y. Yes. All right. Okay, and then we saw these notions of the approximation error, which is how well your hypothesis class approximates the ground truth, and the estimation error, which is how well, let us say, something like ERM approximates the best possible achievable within your hypothesis class. All right. Okay. So now we'd like to see, we'd like to understand two different things. When is it possible to do pack learning, and when is it not possible to do pack learning? So first we'll see a sufficient condition for pack learning using the ideas we've seen so far. Let's try to generalize the essential concepts that we've seen that allow you to show that something is pack learnable, right? So I'll define something called let's very quickly try to recall what we did to show that finite concept classes are pack learnable in the context of classification. What we did was we picked a particular h, any arbitrary h, and saw that if the number of samples is large enough, then the empirical risk is very close to the generalization error that particular h would achieve, and we did this using a simple tail bound, right, a concentration inequality. And then later we use the union bound to say that if this happens for every single h, then it's easy, because you just look at the empirical risk. The empirical risk is a good approximation to the generalization error. So the one that minimizes empirical risk would also be close to the one that minimizes the generalization error. That was the fundamental idea behind that particular proof, right? And that's exactly what we will we'll essentially conceptualize. Okay, so for a given training set, we'll say that the training set S is epsilon by 2 representative for a hypothesis class H if if exactly the same that we wanted happens, which is that the empirical risk achieved by H over this particular training set S is close to the generalization error achieved by this particular H, and that difference is at most epsilon by 2. Okay, and this happens for all hypotheses in the hypothesis class. So RS of H is just the empirical risk, 1 over n summation I equal to 1 to n L of yi comma H of x. This is yeah. I mean, ERM means that you minimize the empirical risk, right?
So then aren't we sticking to the notion of theorem?
Yes.
Then we can generalize it that when we are fixing some algorithm.
So right now I've said nothing else about learnability, right? I'm just introducing a notion. I'm saying that, so effectively, to show that something is pack learnable, I will be using ERM, right?
But it is a property.
What do you mean by pack?
Pack learnable.
Like pack learnable or agnostic pack learnable, I will use ERM to show an achievability because it is one learning algorithm, right?
When we show that exists a pack learnable.
I'm sorry?
When we say that the property is the bound which we have.
Okay,
When we show that there exists an algorithm
correct,
which gives this,
correct.
we can comment that this hypothesis.
That's by definition, right? So all I need to show is that to show achievability, I just need to show that there is some algorithm. It can be my favorite algorithm. If I show that there is one algorithm for which this happens, this can be achieved for every epsilon comma delta, then the hypothesis class is pack learnable. In particular, if I show that ERM achieves this for every epsilon and delta, the hypothesis class is pack learnable. But just because ERM does not achieve this doesn't mean that it is not pack learnable. Okay? To show that something is not pack learnable, I need something stronger, that no learning algorithm can achieve arbitrary epsilon delta f. Okay. All right. So suppose that I was lucky enough to get a training set which is epsilon by 2 representative for H. All right. And then I actually do ERM. So suppose S is epsilon by 2 representative. For this hypothesis class, I'm not saying that H is finite or infinite or anything. It can be anything, any arbitrary hypothesis class. But this is a special training set somehow. And let's say that S is in fact epsilon by 2 representative. Then what can I comment about the performance of ERM? So what is RS of HS? Right. So this is the empirical risk minimizer. Let me be a little more specific. How would this compare to R of H star? Where this is the hypothesis that achieves the least possible generalization error. Let me correct myself a little bit. I want something more. I want R of HS minus R of H star because that's what I'm interested in. Generalization error achieved by the empirical risk minimizer. Yeah. See?
RS of H, RS of H, R of H.
You're saying that RS of HS minus R of H star will be less than epsilon by 2. Why?
R of H.
But why does that mean that it's less than epsilon by 2? R of H star is less than RS of HS. So again, this is an absolute value over here.
Generalization for the
Empirical risk minimizer. Okay, so let me make things a little easier perhaps. Let me just look at this. So this quantity is always non-negative, right? This is greater than or equal to 0 because R of H star is the least among all possible hypotheses in the hypothesis class. If I'm able to get an upper bound on this, it's good, right? Okay. What can I do now? I can write this as R of HS minus R of H star, and I will add and subtract R of H, R of HS, oh sorry, RS of HS, and subtract RS of HS. Okay. So this R of RS of HS is brought over here. Okay, we know that this is at most epsilon by 2, but I really need to know how far RS of HS is compared to R of H star, right? And so let's use what you suggested. I know that RS of HS is less than or equal to RS of H star, right? So this is less than or equal to RS of H star minus R of H star, right? So this is less than or equal to. Now I know that this particular training set S is epsilon by 2 representative for H. So this quantity is at most epsilon by 2, right? Because this absolute value is less than or equal to epsilon by 2. And this is also less than or equal to epsilon by 2. I need an upper bound, right? minus epsilon by 2 is which is epsilon. So if the training set happened to be epsilon by 2 representative, then the ERM would achieve a generalization error which is within an epsilon of the best possible generalization error within this hypothesis class. All right. But of course, this is for one specific training set. I've instantiated a good training set. So then everything boils down to asking, what is the probability that I see this good training set? What is the probability that S is epsilon by 2 representative for H? And that leads us to the notion of uniform convergence. So uniform convergence essentially says that for every hypothesis in the hypothesis class, the empirical risk is going to be very close to the generalization error. Okay. So we say that H satisfies or has the uniform convergence property if for every epsilon greater than 0, delta greater than 0, there exists some number which depends on the hypothesis class epsilon and delta, but does not depend on the joint distribution pxy, such that the probability Rs of H minus R of H is greater than or equal to epsilon for, in fact, I'll say epsilon by 2 for any. So in other words, the probability that S is epsilon by 2 representative for H, or I should say not epsilon by 2 representative, is at most delta. I'm sorry, can you? So this is Rs of H, this is M subscript H superscript UC, just for uniform convergence. This is less than or equal to delta. And this holds true for all Pxy. Irrespective of what the ground truth is, all I'm saying is that the empirical risk is going to be very close to the generalization error for all hypotheses. Cardinality of S is right, true, as long as cardinality of S is at least M H UC of epsilon comma delta.
H of BC takes epsilon comma delta.
Correct. It takes as input the hypothesis class epsilon and delta and outputs some positive integer. No, it depends on the hypothesis class. because this, so I'm not saying that H is even finite. So if H has this property, then it's said to satisfy the uniform convergence property.
Yes, we are saying the number of is a function.
Correct.
Won't it be the same case in the number of samples?
Correct. It depends only on epsilon and delta. Correct.
It is also a function.
Correct. That's true. It is, right? So, and in fact, we saw that, right? In the case of classification, we saw that M is at most 1 over epsilon log size of H divided by delta. But there, it depended on H only through the size of H. So it's an upper bound. If there was some additional structure on H, maybe it's less than that. It would depend on H in some complicated way, right? So some observations. Every finite hypothesis class satisfies the uniform convergence property, because you just need to use a concentration inequality and just use the union bound. Correct. So as we saw, the uniform convergence property is sufficient for pack learnability. So in fact, let me make that statement first. UC is sufficient for, in fact, agnostic The second, which requires essentially the same ideas as we saw for binary classification, but can be generalized further just through a different tail bound, is that all finite hypothesis classes satisfy are
H being an epsilon by 2 representative of H.
correct.
Means H satisfies the uniform.
Can you repeat?
Being an epsilon by 2 representative of H.
Correct.
And S being the epsilon by 2 representative for H being a highly likely event.
Correct.
Makes H satisfy the uniform.
But that's by definition the uniform convergence property. So with so
this means that for that particular hypothesis class and the sample space,
correct.
The empirical risk and the actual risk are
Very close.
epsilon by 2 close.
Yes.
That is a very highly likely.
Correct. If it is a highly likely event, then essentially more than highly likely event, as you let M increase, one way to look at this is that as you let the training size increase, the empirical risk should in fact converge to the true risk for all H, and this happens uniformly
All H
in that hypothesis class. Yes.
suggests that empirical risk is very nice.
Correct. And it's a nice estimate for all the hypotheses in your hypothesis class. It's not only it's not that it works only for some hypothesis. So in fact, a H that satisfies the uniform convergence property is sometimes called a Glivenko-Cantelli class. Just a name.
if NY is sufficient for diagnosis.
Okay, so suppose that I have UC, right? I have a hypothesis class which satisfies the uniform convergence property, right? Now, this means that as long as the number of samples is at least mh of mhuc of epsilon comma delta, the empirical risk for every h is within an epsilon by 2 of this with probability at least 1 minus delta, correct? Now, if we combine this with our previous observation over here, this means that if it is epsilon by 2 representative, then the ERM will return something for which the generalization error is within an epsilon of the best possible generalization error. And that implies agnostic path learnability. Right?
This value of epsilon,
I'm sorry?
when we say epsilon by
Correct.
value of epsilon is
That's a choice, right? You fix, and for every epsilon comma delta, the integer m depends on epsilon and delta. Correct.
then epsilon, it is true for any epsilon.
Yes, we want it to be true for every epsilon and
And if
delta.
we want to do for some small epsilon, approximately, what kind of things we need to get so that
I'm sorry, maybe I didn't follow what you meant.
epsilon is equal to 1 10 power minus.
Okay, 10 power minus 5. Okay.
But the number also is exact.
For that number, the number of samples that you would require could be large, right? Could be like very, very large. Correct. In fact, for finite hypothesis classes, we saw that essentially, or at least in the context of binary classification, we saw that this quantity is at most, let's say, some constant divided by epsilon log size of hypothesis class divided by delta, right? So as you decrease epsilon, let us say it is 10 to the power minus 6, that's the target epsilon that you want to reach, then the number of samples you would require according to this bound would be 10 to the power, would be at least 10 to the power 6. It says that for every epsilon and delta, the probability that S is not epsilon representative is at most delta, right? Another way of looking at, I mean, the ideas over here is essentially the same as the notion that is used in path learnability, right?
Can we say that a hypothesis surely be epsilon? A probability one is
No, right? It's with probability at least 1 minus delta, right? That's what we want. This probability, the probability that S is epsilon by 2 representative should be at least 1 minus delta.
there when we above one when we say that
Correct. Here you mean? Okay.
here we say that training is epsilon.
Correct. It's some particular set of samples, right? It's a property of your training set, of the particular realization of your training set.
There is no notion of
No, here there's no notion of probability. It's purely a property of the samples that you saw, right? The probability that it is, so when is epsilon by 2 so it's a desirable property of a training set.
being epsilon.
That's what is there here, right? That's exactly what we want.
when we say it is only epsilon,
It's a property of the training set, right? It's an event, right? The event that S is epsilon by 2 representative.
and what it is specific for
Epsilon is fixed, right? We're fixing an epsilon and we're fixing a delta.
where epsilon is fixed.
Yes. Yes. Okay. So what we've seen is that uniform convergence is a sufficient condition for agnostic path learnability in general, and all finite hypothesis classes are actually satisfy the uniform convergence property. Now, I have not proved this completely, but it's something you can do. Effectively, all you need to do is use Hoeffding's inequality. Right? This requires you to make certain assumptions about the loss function. Not true for any arbitrary weird looking loss function, but for instance, as long as L of as long as the loss function is bounded, is between some beta and alpha, as long as the loss function is bounded, all finite hypothesis classes, irrespective of what problem it is, whether it's a classification problem or a regression problem, doesn't matter how many classes you have, doesn't matter how you define the loss function, this will satisfy the uniform convergence property. So it's a fairly general result. Okay. But one thing to note is that if something satisfies the uniform convergence property, it is path learnable. The converse is not necessarily true. Just because it is not uniformly convergent doesn't mean that it is not path learnable. So that tells us when is path learning possible, but we'll also see when is path learning not possible. And this is something stronger. What we want to show is that no matter which learning algorithm you use, whether you use empirical risk minimization or anything else, you will never be able to achieve an epsilon delta error. Right? So here's a very well-known result. I will not prove this particular result, but we'll be using this again and again. So it's called the no free lunch theorem. Basically says that you can't have everything for free. Right? So the high level statement is that it is not possible to design a learning algorithm that works well in all possible scenarios. In particular, what it says is that if you have any learning algorithm, it could be ERM, it could be something else, and we'll focus exclusively on binary classification over some set X. Right? So the domain is, for now, let's assume that it is finite. Then suppose that you observe some number of samples which is less than size of the domain divided by 2. Okay. Then in fact you can construct two things. So one is you can construct a function. So you can construct a distribution, a joint distribution, for which for some function the generalization error is exactly equal to 0. Okay. There is some ground truth that achieves 0 error, but then your learning algorithm, if it observes too few samples, in fact less than half of the number of points in the domain, then you will not be able to learn. So these constants are chosen arbitrarily. Basically says that the output of your learning algorithm will achieve a generalization error that is large, and that this happens with some constant probability. right? And here we're assuming that the hypothesis class is in fact the set of all functions on a subset of size 2 times the size of 2 times the number of samples. Correct. So the cardinality of, so what would be the cardinality of H? No. What is the number of functions? Number of binaries. Again, we are looking at binary classification. Yeah. So the size of H is 2 to the power 2 times size of S. Yeah. In fact, the version that we will use is if so suppose that the number of samples that you have is equal to m, all right? Consider any possible x. X such that the size of x is at least 2m, then we can construct some joint distribution, and the hypothesis class is, we can even restrict ourselves to all possible functions from a subset functions from this subset of x of size 2m to 0, 1. Then this particular hypothesis class cannot be learned. Or another way to say is that then if I take this, then no learning algorithm can achieve probability R of Hs less than or equal to R of H star, which is equal to 0, because I'm assuming a finite, I'm assuming that the realizable setting for arbitrary yeah.
So the second point that you did, that 1/7 like quantity, can it be any?
So that 1/8 and 1/7 essentially depends on this 2 that I have chosen over here, nothing else.
You also explain what exactly like it over here, like on a subset of size.
So so you take any subset of x, all right, of size 2 times the number of samples that you have. Okay, it could be the set of all functions from x to 0, 1, but I can even restrict myself to a smaller subset of x. So H is the set of all this here. So my h is the set of all functions h from some x prime to 0 comma 1, where x prime is some subset of x and the size of x prime is 2 times the size of s. Okay. So for instance, if my x is infinite, right, it could be infinite, doesn't matter, but even if I restrict myself to a smaller hypothesis class, where, or a smaller concept class, where the concept class has at most has exactly these many functions, then it's not learnable. I'm sorry?
We want more points.
Correct. So in other words, if you want to achieve a small epsilon delta error, then the number of samples that you have should be at least 2 times the size of x, or at least half the size of x. But what this result also tells you is that if x is an infinite set and h is the set of all possible functions from x to 0 comma 1, then h is not path learnable, right? Because no matter how many samples you have, there is some concept that you cannot learn. It doesn't mean that all infinite concept classes are not path learnable. It means that if the number of concepts is too much, so in this case, this is h is the set of all possible functions from x to 0 comma 1, then h is not path learnable. The concept class is, in this case, in this particular statement, the concept class is the set of all possible functions from x to 0 comma 1. So for instance, if it could be the set of all, so if x is maybe the set of all positive integers, right, then h essentially corresponds to the set of all possible binary sequences. For every little x, you have a value of h of x.
And this subset of
Can you repeat?
cardinality of x is less than or equal to 2 power 2.
So I'm saying that the number of samples is less than or equal to 2 times the size of s.
The
Cardinality of h is 2 to the power the 2 to the power 2 times the number of samples that you have.
Can you take any subset of x?
Correct? Take any subset of x. So suppose you have m samples.
We are collecting all such binary classification.
All possible.
X to 0.
From x to 0 comma 1. Yes.
When we are stating no.
There are infinitely many such functions.
Not in the case of x is finite.
X is finite, yes.
Then the space it contains all bounded space from x to 0.
You could take that, yes.
That is the only choice. Any subset of that.
So even I'm saying that any subset of x, but the subset should have at least 2 times the number of samples, 2 times the size of your training set, at least, for this statement to hold.
The minimum possible space of classifiers is all binary classifiers on x.
Correct.
We can even take
On x prime. So x prime is a subset of x.
is the minimum.
So if you,
The choice.
so in the sense that if you want to know when it doesn't work, then the minimum size of h should be this. This is the smallest h for which it does not. Okay, I don't say that this is the smallest h for which it does not work. If h is this, then it does not work. There could be smaller h for which it doesn't work. Larger h anyway, it doesn't work. You know that, right? If your h is more complex than this, then you cannot learn it. But if it is at least as complex as this, then it is not possible to learn. Yeah.
Like what? Within what x finite?
Correct.
What exactly it will always increase.
That is true. What this is essentially saying is that this gives a lower bound on the number of samples that you require to learn a particular So here what we're focusing on is essentially the set of all, the concept class is the set of all possible functions from x to 0, 1. Okay, let's assume that that is the problem that we're focusing on. So in that particular setting, what this statement is saying is that if you want to achieve some epsilon comma delta error, where epsilon is sufficiently small, delta is sufficiently small, then the number of samples that you require is at least size of x divided by 2. Correct. We don't say anything about pack learnability. That's true. So just this, because we know that all finite concept classes are in fact pack learnable, right? But what this particular statement says is that if you have too few samples, and in fact if it's less, it gives a concrete lower bound on the number of samples that you require. And in particular, it says that certain infinite concept classes are not pack learnable.
If we take sample, then cardinality, then it is
Correct. No. If you take the number of samples to be less than cardinality of x by 2, then you can't achieve arbitrarily small epsilon delta error. That's all that this is saying. If you increase the number of samples, because what does pack learnability say? For something to be pack learnable, you need to be able to achieve an epsilon comma delta error, any arbitrary epsilon comma delta error, for some finite number of samples. The number of samples that you require could be like really large. It could be exponential in the size of x. Doesn't matter. Right?
then when we can say it is not.
A finite concept class is always pack learnable.
Then we can't.
So we can comment that this particular infinite concept class is not pack learnable. Right? So the case where we have finite concept classes is already dealt with. Right? There's nothing to worry about anymore. We know that they are always pack learnable. Right? So now the only ambiguity left is for infinite concept classes. Right? Now, when we have infinite concept classes, we know that some infinite concept classes are not pack learnable. Because if you look at the set of all possible functions, then it is not pack learnable. All possible functions. But then if you go to your homework, there's one specific example where you have to show that there's one particular infinite concept class which is in fact pack learnable. So then how do you say whether something, if I give you an arbitrary infinite concept class, how do you say whether it is pack learnable or not? And what is it? What feature, what property of the hypothesis class makes it pack learnable or not pack learnable? Right? Again, uniform convergence is a sufficient. You had a question.
So, path learnability, the algorithm can be of our choice
Yes,
to minimize the error.
true. In general, yes.
So, even when we are proving that there is an infinite subset of this set of infinite functions that is actually path learnable, the algorithm need not be
Correct. So for this particular statement, it doesn't matter what algorithm you use, you will never be able to achieve anything better than this. Any questions? Okay. So now we'd like to see when is a particular infinite concept class pack learnable or not. And for this, we'll use this particular intuition that if we are looking at the set of all possible functions from some subset to 0, 1, then we need at least subset by 2 number of samples to get arbitrarily small error. Right? That's what we will repeatedly use from this point on. That's question. Okay, I'm sorry? Correct. Correct. Yes. Over an infinite set. Correct. Right? But that's too complicated a class, right? Which one? That's what we'll see. We'll see something more, right? This is sort of a direct result, a corollary of the no free lunch theorem, right? This is too complex a class and it can't be learned. But now if I have something more interesting, right? Maybe I have some class of functions from an infinite set to 0, 1. I want to know whether that is pack learnable or not. Right? It may be pack learnable, it may not be pack learnable. I want to know exactly what property characterizes pack learnability. So it's something in between. Not finite, it is infinite, but it is not as rich as this. Right? Correct. So, any questions? Okay. So we're given the general setup from this point on is the following, that we have some hypothesis class, we have a domain set which is infinite. So we look at X infinite, and we will specifically look at binary classification. Right? And okay, so this is the setup that we will use, because if I take X to be finite in the context of binary classification, then it's always pack learnable. Because then the total number of functions from X to 0, 1 is at most 2 to the power size of X. So that's not interesting because I know that it is pack learnable. So I'm looking at something very specific here. For instance, this could be the set of all possible hyperplanes in or linear classifiers in R2. That's one example of learning a binary classifier. Example. in R2. So basically h of x is equal to 1 if some A transpose x is greater than or equal to 0. This is all those classifiers that pass through the origin. 0 else. Or more generally, if this is A transpose x is greater than or equal to some B. It's a function from R squared to 0.
To visualize the which you are taking set from
I'm sorry, it's
subscale. Previously, you are saying the consider function set of x to the
correct. I mean, that's, we'll use it later. We'll see how to use it later, right? But this is, let's say, one prototypical example that you can have at the back of your mind. This is an example of an infinite concept class, right? Because you can choose. Now, what is this parameterized by? This class of functions is parameterized by A and B. So 3 real numbers, A1, A2, and B. So right now I'll define certain notions and we'll see how they're particularly useful. So let's say that we're given a hypothesis class H and some subset of X. Let me denote this by X subscript M. You take any subset with exactly M elements. So let's say that this is equal to some x1, x2 up to xn. If you pick any M elements from this, then the restriction of H to xm to xm is basically the set of all functions h of x1, h of x2, h of xm. Now note that this xm is a finite set. So if you think of all possible functions from xm to 0, 1, there are at most 2 to the m possible functions, right? And this particular h induces some set of functions on xm, and this set of functions is what I call the restriction of h to xm. So in other words, it could be possible that when I restrict myself to only this specific subset, two functions which are different in h essentially boil down to the same function in x. Which one? A vector can be viewed as a function, right? So these are the evaluations on this particular, on it's from m to 0, 1. 1, 2, 3 up to m to 0, 1. Let's see some specific examples perhaps. Let's take something like a really complex set of functions. Say h is the set of all possible h of x, which is equal to alpha to the power x, where alpha can be any arbitrary real number. Okay, so it's all possible exponential functions with arbitrary alpha. So each alpha specifies one function which tells you the rate of increase or rate of decrease with respect to x, and h is the set of all such functions. Okay, now let me take x subscript m to be, say, 0, 1. Only 2 points from the entire space of reals. I'm picking up 2 points, 0 and 1, and nothing else. All right. In fact, let me take something different. Let me take 0, 2. All right. Now I'm interested in functions from xm to 0, xm which is equal to 0, 2 to 0, 1. Right? Sorry, in this case, not just 0, 1. These are functions from R to R. So these are functions from 0, 2 to R. Right? So this is a finite set. The domain is a finite set. The range is potentially all of R. Right? So what does this space of functions look like? All possible functions from 0, 2 to R. I know, but it has a very specific structure, a very simple structure. Partition product of?
Set 0,
It is for
I'm sorry?
the function is the
Let's forget about this for the moment. Okay, this specific h. Let's not worry about that. Okay. I want to know what is the set of all possible functions from 0, 2 to R. All possible functions, not restrictions of h or anything like that. What do you need to specify a function from this to R? Correct. You just need to specify two different values. What is h of 0 and what is h of 2? Nothing else. Correct. So in other words, the set of all possible functions from xm to R is in fact, it's isomorphic to R2. So it's a set of all possible pairs of real numbers. Correct. So in this case, every function corresponds to a pair of real numbers. Right? In general, if I give you an arbitrary set, let's say xm, and I want to know what is the set of all possible functions from xm to some set y, what does it correspond to? Set of m values, and each value is taken from y. Right? So this is the same as specifying all possible evaluations of over each of these elements of x1 through xn. Does that make sense? For this specific example, what does it correspond to? What would be the restriction of h to 0, 2? Okay, so if I restrict myself to this particular h, what can I say about h of 0? It's always going to be 1, no matter what happens, except, yeah, it's always going to be 1, right? No matter what alpha you choose. What about h of 2? It's alpha square, and this is always going to be, yeah, so it's always going to be non-negative, right? So the restriction of h to xm in this case is, let me denote this as h subscript xm. This is in fact the set of all 1 comma alpha square, alpha belongs to R. And one thing to note here is that there are multiple functions. So for example, 2 to the power x and minus 2 to the power x, both when restricted to h correspond to the same function. Right? So even though the space of functions that you had, the space of hypothesis that you originally had was like really large, when restricted to a much smaller subset, it boils down to something much smaller, potentially much smaller. So let's maybe see one more example. Suppose my h is the set of all possible h of x, which is equal to 1 if x is, say, less than or equal to alpha, and 0 if x is greater than alpha. Okay, so this is my h. And I'll take my x m to be, say, 0 comma, let's say 0 1 2. Right? So my restriction of h to xm is nothing but set of all pairs h of 0, h of 1, h of 2, all possible evaluations. But what possible values can this take in this specific scenario? Yeah? Each h of I can be 0 or 1, right? But can it take all possible combinations of 0 and 1? That's the question. 0 cannot come before 1, right? Because it's 1 if x is less than or equal to alpha. It's equal to 1 if x is less than or equal to alpha. So if h of 1 is equal to 1, then h of 0 must be equal to 1. So what are all the possible combinations it can take? I can have 0 0 0, right? Can I have 1 1 1? Can I have 0 1 0? I can't, right? I can have 1 0 0. I can have 1 1 0, and of course 1 1. Is there anything else that is possible? nothing else, right? So if I restrict this particular h to this particular xm, then the number of functions that I get is just 4, right? Is that okay? All right. So we'll continue in the next class. So essentially, why do we want to do all of this? Recall that if we are ever in a scenario where the number of hypotheses is the set of all, or the hypothesis class is the set of all functions from some subset to 0, 1, then we have a lower bound on the risk that any algorithm can possibly achieve, right? So to show something, to show that some particular hypothesis class, infinite hypothesis class, is not path learnable, what we'll do is we look at restrictions of the hypothesis class to finite subsets. Right? If it so happens that the restriction to all possible finite subsets is the set of all possible functions from this finite subset to 0, 1, then the number of samples that you need is at least half the size of this subset, and therefore for every arbitrary subset this happens, so it's not path learnable. That will allow us to say when it is not path learnable. But then we later see that that's also sufficient condition. That is, if there is some finite subset for which the set of all possible, so that the restriction of h to this particular finite subset is not the set of all possible functions from the finite subset to 0, 1, then it's a scenario where it is path learnable. So that we'll see that is one combinatorial way to characterize the richness of a particular class of functions. So in this specific case, all right, suppose that h were the class of all functions from R to 0, 1. I take any finite subset of R and I restrict h to this subset. What would I get? So let's consider a scenario where h is equal to set of all functions from R to 0, 1, and I take xm to be any finite subset, any arbitrary x1 to xm, all right, subset of R, and I look at the hypothesis class restricted to xm. What would I get? Correct. So it would be the set of all possible functions from xm to 0, 1. Right. So no matter which subset I choose, it's always going to give me, the restriction is always going to give me the set of all possible binary functions from xm to 0, 1. Right. And we know that in this specific case, this is an example of a hypothesis class which is not path learnable. So we'll connect this with this notion. So we'll quantify richness as the smallest, using the smallest subset for which the restriction of h to this subset is not equal to the set of all possible functions. Hxm is finite, yes. It's at most 2 to the power n, right? What is path learnable? What I want to comment on is path learnability of h, not hxm. We'll see that. Okay, so let's stop here.